Imagine standing inside a cramped engine house in the summer of 1776, somewhere along the marshy banks of the River Lea in East London, as a team of men heave a freshly bored iron cylinder into position. The air reeks of malt and grain from the distillery next door. The cylinder, just 18 inches across, has travelled over 100 miles by canal, barge and wagon from the ironworks of Shropshire. The men handling it know they are assembling something that has never been tried in this city before. Not a lumbering Newcomen atmospheric engine, but a machine built on an entirely new principle. A machine designed by a Scottish engineer named James Watt. A machine that will consume barely a quarter of the coal its predecessors demanded. And when that piston makes its first stroke, when steam hisses into the separate condenser for the first time in London, the men standing in this engine house at Stratford-le-Bow will witness one of the earliest demonstrations of the technology that will remake the world. To understand how this engine came to be erected in such an unlikely corner of England, we need to travel back several years and several hundred miles to the northwest, to the workshops and foundries where its story truly begins. East London in the 1770s was a landscape caught between two ages. The parishes east of the city walls, Bow, Stratford, Bromley-by-Bow, sat along the River Lea and its tangled network of back channels, a web of tidal waterways that had powered mills since the time of the Domesday Book. Tide mills ground grain along these banks. Distilleries turned that grain into spirits. Dye works, calico printers, and small metalworking shops lined the riverbanks, drawing their water and their power from the ancient current. Barges carried coal, chalk, timber, and wheat up and down the Lea navigation, connecting these East London workshops to the broader economy of southern England. Wharves crowded the banks at Stratford and along the Channelsea River, handling everything from general cargo to specialized loads of stone and fuel. It was a working landscape, industrial in character long before anyone coined the word, and it was here, among the distilleries and mills of Bow, that one of the most important machines of the 18th century would first prove itself to a London audience. The engine that arrived in Stratford-le-Bow that year had its origins not in London, but in the restless mind of James Watt and the ambitious workshops of Matthew Boulton. Their partnership, formalized only the year before in 1775, was one of the most consequential business arrangements of the century. But the road to that partnership had been long and tortuous, shaped by frustration, financial difficulty, and the maddening gap between a brilliant idea and the practical means to build it. Watt had conceived the principle of the separate condenser more than a decade earlier, in 1763, while repairing a small model of a Newcomen atmospheric engine at the University of Glasgow. The Newcomen engine, which had been pumping water from mines since 1712, worked by admitting steam into a cylinder, then spraying cold water directly inside to condense that steam, creating a partial vacuum that allowed atmospheric pressure to push the piston down. It was an ingenious machine, but a desperately wasteful one. Each stroke required the cylinder to be heated by steam and then cooled by the injection water, over and over again. An enormous quantity of fuel was squandered, simply reheating the cylinder walls after every condensation. Watt's insight was elegant. Rather than condensing the steam inside the working cylinder, he proposed drawing it off into a separate vessel, the condenser, where it could be cooled and condensed without ever chilling the cylinder itself. The cylinder could remain hot, the condenser could remain cold, and the fuel savings would be extraordinary. In theory, the engine would use roughly 75% less coal than a comparable Newcomen machine. It was a transformative idea, but turning it into a working engine proved agonizingly difficult. For years, Watt struggled with what he called the villainous bad workmanship of his Glasgow artisans. The technology of the 1760s simply could not produce the precision components his design demanded. A piston that did not fit snugly inside its cylinder leaked steam. A cylinder that was not perfectly round wasted power. Watt built model after model, partnered first with the ironmaster John Roebuck at Canal, and watched his experimental engines fail to perform, as theory predicted. The concept was sound. The execution was not. What Watt needed was access to the finest workshops and the most skilled metalworkers in Britain. He found them at Soho, Matthew Boulton's Soho Manufactory, 2 miles north of Birmingham on the Wolverhampton Road, was by the early 1770s one of the most remarkable industrial establishments in England. Boulton had built it from nothing on what had been a barren heath, erecting a series of roomy, interconnected workshops that employed between 700 and 800 people. They produced buttons, buckles, watch chains, silverware, ornamental metalwork in brass, steel, and ormolu, the full range of what Boulton called the products of metallic artists. Distinguished visitors came constantly: princes, ambassadors, philosophers, and foreign dignitaries, all eager to see the manufactory that was spoken of as one of the sights of England. Boulton employed the finest craftsmen he could find, French, Italian, and English, and paid them generously to ensure the highest quality of workmanship. His tools were precise, his organization was meticulous, and he was fascinated by steam power. Boulton had himself experimented with fire engines, corresponding with Benjamin Franklin about boiler design and valve mechanisms as early as 1766. He maintained a model engine at Soho and made careful notes of his experiments. When he learned of Watt's separate condenser, through their mutual friend Dr. William Small, he immediately recognized both its brilliance and its commercial potential. After Roebuck's financial collapse, Boulton acquired his share of Watt's patent, and in 1774, Watt finally moved to Birmingham. At last, he had access to the facilities and the practical experience of craftsmen who could translate his designs into working metal. But even the skilled hands of Soho could not solve every problem. The critical challenge remained the cylinder. Watt's engine demanded a cylinder bored to unprecedented accuracy. The piston had to seal against its inner wall with minimal leakage, far tighter than anything a Newcomen engine required. The answer came from an unexpected quarter: the cannon foundries. John Wilkinson, an ironmaster known to his contemporaries as Iron Mad Wilkinson, had developed a new boring machine for the manufacture of cast iron cannons. Unlike the cantilevered borers then in common use, Wilkinson's machine supported the boring tool on a shaft that extended through the entire length of the cylinder, held firmly at both ends. This produced a bore of extraordinary accuracy and smoothness. When Boulton learned of Wilkinson's technique, he immediately saw its application. In 1775, while Watt was in London securing a 24-year extension to his patent, approved by an Act of Parliament in May of that year, Boulton commissioned Wilkinson to bore a new cast-iron cylinder of 18 inches diameter. When Watt returned to Soho, the cylinder was waiting for him. It worked brilliantly. Now Boulton and Watt could build engines that actually performed as the theory promised. And they moved quickly. In 1775, Watt designed 2 large engines simultaneously. The first was for the Bloomfield Colliery at Tipton in Staffordshire, a coal mine that needed a powerful pump to keep its workings dry. The second was for John Wilkinson's own ironworks at Broseley in Shropshire, fitting, given that Wilkinson's boring machine had made the engines possible in the first place. The Bloomfield engine was completed in March of 1776. Wilkinson's engine followed the next month. Both performed superbly. But Boulton was not content with 2 engines. He was a businessman as much as an engineer, and he understood that the commercial future of the partnership depended on demonstrating the engine's capabilities as widely as possible and as quickly as possible. There was a third engine already in hand, commissioned by Cook and Company, operators of a distillery at Stratford-le-Bow in East London. Boulton urged its completion with particular enthusiasm. a working engine in London, visible to the merchants, industrialists, and men of influence who congregated in the capital, would be worth more than a dozen engines hidden away in Midlands collieries. London was the shop window of the nation. The Stratford-le-Bow engine was a small pumping engine, fitted with an 18-inch cylinder bored by Wilkinson's machine. Its purpose was to pump water at the distillery, a task that had previously been accomplished by horsepower or by the fitful energy of the tidal Lea. The engine's components were manufactured across a network of workshops scattered through the English Midlands. The cylinder came from Wilkinson's foundry. Precision parts, valves, pipe fittings, the regulator mechanism, were fabricated at the Soho Manufactory in Birmingham. The great beam, the chains, the pump rods. These heavier structural elements were cast or forged by local ironworkers, according to Watt's detailed specifications. Boulton and Watt's practice in these early years was not to manufacture complete engines themselves and ship them as finished units. Instead, they designed the engine, specified every dimension, supplied the critical components, above all the cylinder and the separate condenser, and then supervised the construction and erection of the engine at the customer's site. They licensed their patented improvements and charged the customer a royalty, based on the fuel savings the new engine achieved compared to a Newcomen machine of equivalent power. This was a shrewd business model. It minimized Boulton and Watt's capital outlay, spread the costs of construction, and tied their income directly to the superior performance of their design. Getting the engine components to Stratford-le-Bow was itself a considerable logistical undertaking. The cylinder, cast at Wilkinson's works in Shropshire, had to travel by barge along the river network and canal system that was just beginning to knit together the industrial regions of England. Components from Soho in Birmingham would have followed a similar route, along the Birmingham Canal, then southward toward London. The final leg of the journey brought the heavy iron castings down the Thames and up the Lea navigation into the heart of East London's industrial district. The erection of a Boulton and Watt engine was a methodical process that typically took several weeks, and we have detailed accounts of how it was done from the installation of similar engines in this period. First, the engine house had to be prepared, a sturdy brick structure built to contain the cylinder, the beam, and the working mechanism. A brick platform or foundation was laid for the cylinder. The great wooden beam was hoisted into position overhead, supported by the engine house walls, and the chain linkages, called martingales, were attached at the cylinder end. Then the cylinder itself was set in place on its foundation. The inner bottom plate was drilled for holding down screws, tapped and secured. The cylinder was aligned and fixed. The piston, carefully fitted to match Wilkinson's precision bore, was lowered inside. The separate condenser, the heart of Watt's invention, was installed below or beside the cylinder, connected by pipes and valves that allowed the spent steam to be drawn off and condensed without cooling the working cylinder. The air pump, which maintained the vacuum in the condenser, was fitted and connected. The boiler, a great copper or iron vessel, was bricked into its own setting nearby, with a coal-fired grate beneath it. Pipes connected the boiler to the cylinder through a system of valves that controlled the admission and exhaust of steam. Each of these steps required careful attention. The joints had to be sealed. The valve timing had to be adjusted. Watt himself often supervised the erection of these early engines, and the Stratford-le-Bow installation was no exception. Records indicate he personally oversaw the work. He was a meticulous and often anxious man, deeply aware that every engine that left his drawing board carried his reputation with it. A single failure, a single engine that consumed more coal than promised, could undermine the entire commercial enterprise before it had properly begun. By the summer of 1776, the Stratford-le-Bow engine was working. Steam rose from the boiler, passed through the steam jacket that surrounded the cylinder, another of Watt's innovations, designed to keep the cylinder walls hot, and entered the cylinder below the piston. The piston rose. A valve opened, and the steam was drawn into the separate condenser, where a spray of cold water collapsed it back into water, creating the vacuum that pulled the piston back down. The beam rocked. The pump rods descended into the well. Water surged upward. The cycle repeated, stroke after stroke, with a smooth and steady rhythm that no team of horses could match. The fuel savings were immediately apparent. Where a Newcomen engine of similar size would have consumed enormous quantities of coal to do the same work, Watt's engine sipped its fuel with remarkable economy. The separate condenser meant that very little heat was wasted in the endless cycle of heating and cooling. The steam jacket kept the cylinder at working temperature. Wilkinson's precision bore meant the pistons sealed tightly, losing almost no steam past its edges. The engine delivered more work for less coal than anything London had ever seen. Word spread. The following year, in 1777, the great engineer John Smeaton, who had himself spent years improving Newcomen engines and had built dozens of them, some in the 100-horsepower range, made a personal visit to Stratford-le-Bow to inspect the Boulton and Watt engine. Smeaton was perhaps the most respected practical engineer in England at that time, and his opinion carried enormous weight. Matthew Boulton, reporting back to Watt, noted with a mixture of satisfaction and wariness that Smeaton had examined the engine closely. Smeaton's own engines were 3 times less efficient than Watt's design, and although he initially believed that where coal was cheap, his Newcomen improvements might still be competitive, the evidence of Stratford-le-Bow was difficult to argue with. The Watt engine was simply better. The impact of this single engine rippled outward through London's industrial community. Within a year, Messrs. Cook and Company, the very same firm, or closely associated, had a Boulton and Watt engine installed at their brewery at Stratford-le-Bow, paying £200 for a small 18-inch cylinder engine. The London breweries, great consumers of power for grinding malt and pumping water, began to take serious notice. Henry Goodwin's Red Lion Brewery followed in 1784 with a 4-horsepower Boulton and Watt engine, replacing the 4 actual horses that had previously driven their grist mill. Whitbreads purchased an engine the same year. Calvert's followed a year later. Barclay Perkins 4 years after that. Steam power had arrived in London, and the distillery at Stratford-le-Bow had been its proving ground. What makes this story remarkable is its ordinariness. The Stratford-le-Bow engine was not a grand demonstration piece. It was not erected before crowds of dignitaries or celebrated in the newspapers of the day. It was a small pumping engine, installed in a working distillery on the marshy edge of East London, designed to do a practical job more efficiently than the methods it replaced. And yet this quiet practical success was precisely what Boulton and Watt needed. Every engine that worked reliably, every ton of coal saved, every satisfied customer who told his neighbours, these were the building blocks of a revolution. By the 1780s, steam engines were becoming common in London's manufactories and workshops, and the confined, crowded urban environment of the capital favoured compact, efficient designs over the sprawling, coal-hungry Newcomen machines of the past. The men who erected that engine in the summer of 1776, who drilled the bolt holes, sealed the joints, adjusted the valves, and stood back as the first stroke of steam set the beam in motion, could not have known what they were starting. They were skilled workmen doing a job, following specifications drawn up by a Scottish engineer and financed by a Birmingham manufacturer. But the machine they built in that engine house beside the River Lea was one of the first 4 Boulton and Watt engines ever constructed. It was the first of its kind in London, and the principles it embodied, the separate condenser, the steam jacket, the precision bored cylinder, would power the factories, the mills, the breweries, and eventually the railways and steamships that transformed Britain and the world over the next century. The age of steam did not begin with a single dramatic moment. It began in places like Stratford-le-Bow in the summer heat of 1776, with the quiet, steady stroke of a piston in a well-made cylinder, doing useful work.